So yeah, welcome to the second part of the talk tutorial, Sandbox for the Blackbox. So in case you haven't had a chance to get a link for the slides or the references, so here is the link again, the same web page with all the set of references and the slides in PDF. Okay. Okay. So yeah, if you attended like yesterday Andrea's talk, it ended on the note that we need to understand and study learning dynamics. So this is a perfect segue for today's talk. So before we directly get there, so just a quick recap. So yesterday we saw that we would like to use this framework in order to understand these three fundamental questions, right? Like what do these models represent, and how do they learn, and in particular, how do they generalize? So yesterday we focused on the first part where we looked at uh, the representative power of these models. So in particular, the main question that we were interested in was given a set of parametric functions, does there exist a realization that can construct or solve this task? So that was the what we saw yesterday for various classes of architectures, both RNNs and transformers. So today, and just to overall recap, we saw how we did this using like various set of tools one could use, both from the upper bound and the lower bound. And later then we saw what are the implications in terms of the design trade-offs and comparing how these architectures fare and how we could further improve based on these insights. Okay, so today we'll be talking about the other equally and if not more important part of how traditional learning-based methods get there, and in particular, and finally, briefly, I will touch about what are some generalization properties these solutions exhibit. Okay, so that's like the outline for today. Okay, so let's start with the second part where we would be focusing on learning dynamics. Okay, so again here, if you recall the setup, so since we are considering some structured sequential data, so these are like some of the data models that we would be focusing on today. One is the Markov, and there is a topic model and another model called factual recall. And on the model side, we would be predominantly looking at transformers. And for the question of how do they learn, we'll be looking both at the optimization landscape as well as the learning dynamics. Okay, so that's the outline. So let's start with the Markov part. So this is predominant. Okay, the style for today's talk is slightly different from yesterday. So yesterday, if you remember, like I was focused more on the various set of tools people use and so forth. But comparatively, as you would see, the number of works or literature in the learning dynamics parts are relatively sparser. So here I would go into in more depth analysis of how various analysis are done. Okay, and in particular, like among the existing literature, Markov is the one that received like significant attention, and there have been a lot of interesting works with some of my works included as well. And so will be spending a decent amount of time for like next 30-40 minutes on the Markov part, going in detail about how learning dynamics happen in this regime. Okay. So, and why specifically Markovian, as I alluded to yesterday, so it's like one of the principled way to look at languages. So as you know, languages exhibit many kinds of structures and like grammar, syntax, so forth, but also to some extent they're Markovian in the sense that if you know the past few characters in a word or maybe past few words in a sentence with reasonable accuracy, you can predict the next one. And this kind of inspiration has been there for many Markovian study of languages going all the way back to Shannon in his original information, the paper that gave rise to information theory. And so that's like the overall motivation why we use this Markovian sandboxes. Okay, and so that's for the motivation. And the overall recipe, as we would see for this part of analysis, is that first empirically we observe if you run these gradient based methods and so forth on this task, what are empirically some structures learned by these models. And we use this as some kind of an inductive bias when you're doing analysis, because analyzing it for the full model is very complicated. So you parameterize your solutions using these special structures so that there's both tractability as well as you derive meaningful insights. And we do this for both flow or gradient descent depending on the circumstance. Okay, so that's the overall recipe. And with regards to the overall outline here, even inside Markov, if you look at Markovian processes, like they have an intrinsic order, right, or the memory. that you can think of it as like a one knob that you can turn on the input side. On the model side, the knob that we turn is the depth. Okay, it's the number of layers of the model, and we see how an interplay of these two gives a very rich landscape of Markovian learning that we'll see in the next couple of minutes. Okay, and so the outline is, first I will start with the most basic setting to build our muscle slowly, which is the first order Markov chain and a single layer transformer. Okay, this is the most basic setting you can imagine. And then I would slightly increase the depth, keeping the memory same. We would study two layer transformers with again first order Markov chain. And then we consider the general case, what happens if you have generic kth order Markov chain. Okay, depth could be whatever. So this is the overall outline. So let's start with the basic setting, which is a first order Markov chain with a single layer transform. Okay, so here the main takeaway, as you see, is that there is a very surprising result that we observe is that even in this most simplest setting, you can show that provably first order even single layer transformers can provably fail to learn on there's a single first order Markov chains that we'll see, which is a very actually indeed a surprising phenomena. And we see why this happens, in particular how the Markovian data properties and as well as the initialization of your gradient flow make they play a very, very key role in the learning dynamics, which translates to this surprising insight. So that's like the overall takeaway from this part. So yeah, let's start with looking at how the inputs look like. So for a first order Markov chain, just for a quick recap that you might already be familiar with. So let's say there are only two states, like 0 and 1. And from 0 to 1, you flip with probability P, and 1 to 0, you flip with Q. Otherwise, you stay in the state. Much more formally, you can think of it as a Markov chain generated from some stationary distribution in the beginning, and then you apply the same transition. And for this, it's easy to compute the stationary, is like Q by P plus Q and P. And so this same transition diagram could also be written as a matrix, right? Like 1 minus P is the self transition, and P is the flipping probability. Okay, so here the key quantity to keep in mind that I would repeatedly refer to is this term P plus Q. Okay, as you see, this overall signifies some notion of switching. So this is what I would refer to as switching probability, though it's not technically a probability, but this I call it like a switching probability. Okay, and so this is how the input structures, the first order Markov chain is that we consider. And now going to transformers. Okay, what is depth one transformers? So what is the architecture for transformers? Okay, unfortunately, these are too complex for us to solve, but we consider the classical, again, the architecture that we saw yesterday, which is starting with a sequence of tokens, like say x1 to xn. There is an embedding. Then there's a key component, which is the attention mechanism that attends causally to the past. And then you do all point-wise operations. Okay, FF is the feed-forward neural network. Then you pass it through some linear layer to get kind of a logic. Okay, this gives you like the indication of probabilities. And then finally, you apply some softmax function or so forth. In this case, sigmoid is fine, so that you get the probability for the next token. Okay, so this is the full architecture. Okay, and much more, you can write this more mathematically as well, the equations, like you are in this case, remember you are taking a binary sequence, so your state space is binary. So the embedding could be written like a token embedding plus some positional embedding. I'm just giving a rough overview. You don't really need to know what's exactly going inside, just give a high level overview. And the attention mechanism, takes a skip connection plus a weighted combination of the past. So this is at an index n, right? You look at all the indices in the past and you weight them with some value, attention scores and a value vector. Then there's a feed-forward neural network, which is a one-layer ReLU. And then you compute the logics using some linear transformation. In this case, you just need a real number because it's a binary thing. So you just need to predict one symbol probability. That suffices, right? Because the other one is just 1 minus that. So finally, you compute. So this f theta is the prediction probability, meaning given the entire past, the probability for the next token being 1, given the entire past, is some parametric probability, right? Because it depends on all these parameters, and this is given by sigmoid of this logic. So this is just a rough overview of how the architecture looks like. So this is the architecture that we consider, like a one-layer transformer in full generality. And the core component, as I was saying, is this attention block. Okay, attention, and there's a final logic layer. Okay, and here we consider two scenarios, which is called, one is called weight tying. So it's a very popular practice. Popular thing in practice is that where people use the same matrices or the parameters for the linear and the embedding layer. If you think about it, they're just transposes of each other, because in an embedding, you start with something and you embed in high dimension. Whereas for this, you have some embedding and you want to get back to your vocabulary size, right? So you do it's just a transpose of each other, and people typically take the same matrix for both these settings. That's called weight tying, okay? And no one really knows why, like the exact reason. There are some minor reasons, but I never understood why. But in case if someone knows, please let me know. But anyway, this is something people do in practice. And there is another scenario where there's no, I mean, they could be free, okay? They're like independent parameters. So that's the no weight tying. So we consider both the scenarios, okay? And yeah, so that's the overall transformer. And here the theta denotes all the set of parameters that you saw inside, okay? These weight matrices, embeddings, everything, okay? Token embeddings. Just one theta, I'm denoting everything together. Together, we saw the input is a first order Markov chain that is generated according to this transition matrix. Then you feed it to the model, and the model at each position, it predicts the probability for the next token. Okay, so that's how the model works, right? It causally predicts at each and every position what is the probability predictive probability for the next token. And so, okay, yeah.
Can you go back to the yeah, even further? Yeah. So here, basically, this just looks like one type of feed-forward neural network, right?
After this, yes, but before this, there is a sequence-to-sequence mapping, because at every position n, you're looking at the full past. If you look at this equation, how I get this embedding vector is you take a weighted combinations of the past, I is equal to 1 to n. Summation is over the past indices, the attention score, which lies strictly between 0 to 1, and they all sum to 1. Okay, it's like the probability, it's like a probability, but and the value vector at that position. So it's so this is where the causal aspect is. If you take out this, then yeah, it's like a feed forward and some linear and stuff, so forth. But there's a causal aspect here, and also there is some notion of causal aspect, because at every position, you add something called positional embedding. So it's like encoding the notion of position information there. So that's what they do in transformers, because I laid out the equations for you in like a sequential manner so that it's easy to understand. But the way they train transformers is you feed the full sequence in one block, one go. Okay, because that's to allow for parallelism. But functionally, this is what it does. I laid it out to illustrate the sequential aspect of the model. Okay, so in this case, we are just taking some, we just say there's some trainable positional embedding. There are, again, there is a lot of variations in that, but for now, just take simple. Okay, so we saw the setup. Okay, I showed you both the model and the input data structure, but that's not the full part of the story, right? You need to train the model on some laws. So the laws that we consider is the classical next token prediction law. So what does it mean? So mathematically, you can write this as this like a, okay, the expression looks fancy, but the idea is very simple. It's just the cross entropy loss between your next token, xn plus 1, and your prediction probability. So this is like the, you can say it's a log likelihood, right? Just log likelihood, negative log likelihood. So that's the overall loss. And you, since this is a random quantity, right? Because everything is random, the sequences are random, you take expectation and you sum it across all the positions and average. So this is your next token prediction loss. And in an ideal scenario, it's not hard to see that the where you can absolutely minimize is it when your prediction probability exactly matches the underlying Markovian kernel, right? So that's when this is the loss is absolutely minimized, okay? And so if you take a look here, there is some catch. The underlying model is first order, so the transition is only dictated by xn, okay? Just the past token. But for the model, in principle, it could take the full past into account. So it has to figure out through training that the dependency is only on the first order part. Okay, so, but the model doesn't know it because I'm not telling the model that it's a first order. I'm just feeding the sequences and I'm training the model on this loss. So the hope is that the model figures out that it's only a first order transition. And it doesn't need to take the full past into account. So we'll see what happens, but this is the idealistic scenario that we hope for, okay? And, okay. So as I said, this is the ideal scenario we hope for, but surprisingly, it turns out that even in this simple setting, the single layer transformer can actually provable to learn first order Markov chains. Okay, so what do I mean by that? So it turns out that the loss landscape for this looks something like this. Is just a cartoon of it. I will go into details. There is some global minima on this, okay, which is good to know. But also turns out that often in practice it gets stuck at some local minima, okay, some theta pi under certain conditions, okay. And if you change those conditions a bit, it turns out that the same point behaves like a saddle point. So possibly paving way for it to escape it during training and maybe go to global minima. So this is like the overall flavor of results that we will show here, okay? And what exactly and how exactly does it happen? So let's take a look. So here,
I can ask a question before you go on.
Told that these two parameters are shared, both the embedding and the final linear layer. So if there is weight tying, so this is how the loss landscape looks like. So here theta star is that first good to know is that there is always a global minimum on this loss surface, meaning you can absolutely represent the first order Markov kernel using your transformer. Okay, so there's always global minimum. It's not that we are cheating. Okay, in this parameterization, you can always represent a first order Markov chain, which is not hard to see, right? Just a linear function. So for all this transition, all this P and Q, there exists global minimum on the loss surface. But that's not the interesting part, right? So it turns out that if your switching is greater than 1, okay, you can mathematically show that there are some bad local minima on this loss surface, for which, if you look at the prediction, it's just the marginal, okay? So let's take a moment to parse this. So the right-hand side is just some constant, right? It's a marginal probability. But if the left-hand side, if you look at, in principle, it's a function of the entire sequence. And it's predicting something constant. That means it just is ignoring the full sequence. It's basically at every position, it's just outputting some constant probability, which is the marginal probability. Okay? And it turns out that this is a bad local minima. Okay, I'll get into the precise statement just in a few minutes. Okay? And the same picture, if you remove weight tying, it turns out that the same point turns out to be a saddle point, turns into a saddle point, okay, satisfying again the same properties. The prediction probability is again the marginal, and the condition again the same, but the same point behaves like a saddle point, okay. So more precisely.
Hi, Ashok, I have a question. Can you hear me? Hello. Yeah. So my question is actually, yesterday at the end of the talk, you told us how single layer transformers couldn't get an induction head. In the extreme case where, I make one of these P's or Q's 1, then, and I maybe make the alphabet 3 letters rather than 2 letters, which is what you have here, then this is basically the problem of trying to express an induction head, right? Because if there's 0, you should either get 1 or 0.
A good question, actually. So the small subtle difference here. So the Markov chain that I'm considering here is a global Markov chain, meaning there is some fixed Markov transition matrix, and I'm sampling from this. All the sequences, Markov sequences come from this fixed transition matrix, okay? So later I will cover in the talk. So this kind of an induction head or in-context learning comes about when your data comes from some kind of like a mixture distribution, okay? That's the setting where it's more relevant, okay? I will touch upon this, okay, just the second part. And this point becomes a bit more clearer there, where we will see how depth 2 comes, goes about capturing the same. But as you said, I think this result has to be viewed in parallel to the yesterday's results, because yesterday's result is more about induction head. So here, there is no really a notion of induction head that we need, because it's a first order Markov chain. So it suffices to just capture the previous one, okay? And also you just need to learn you see the global minima, you just need to learn the transition kernel. So there is no in context as such here, because all the sequences are sampled from a single stationary transition matrix. All you need is to represent this transition kernel function. Okay.
Okay. Thank you.
Okay. Okay, yeah, great question. So as I was saying, yeah, if you remove weight tying, this point turns out to be saddle point. So mathematically, what you can show is that if your switching is greater than 1 and there is weight tying, you can explicitly construct points theta pi in this parameter space so that this is a bad local minima, meaning the loss is strictly greater, where the prediction probability is the marginal, and you can show that the loss exactly correspond to the entropy of this stationary distribution, right? The Shannon entropy, and you can show, yeah, stationary point, so forth. So that's like the main technical result that you could show. And if you remove this weight tying, it turns out that under the same conditions, the same point theta pi, you can show that it's a saddle point. Okay, so that's like the overall main theoretical result here. And just to give you a brief intuition about how we go about constructing or, yeah. So very good question. This will just come in 5 minutes. So it turns out that there are, okay, and there is a reason why in practice you don't see them, that is answered by the dynamics part. Here, okay, that's a good point also you raised. Here I'm only showing existence, okay? I'm saying that if, yeah, this conditions happen, there is a local minima, and if not, the same point goes to saddle point. So this does not preclude the possibility that there could be bad local minima here or here. In fact, there are, but there is a reason why I'm focusing on this the set of results, because that's what we empirically observe. And the later part, the dynamics fully justifies why this happens. Okay, at this point, you can think of, we are looking at a static point of view. I'm just looking at the loss landscape. Okay, I'm not really talking about how movement happens on this loss landscape, but I'm just giving you a very static picture of how it looks like. Okay, so just to give you some intuition about how we establish. So the main idea here is that, as I was saying before, so if in this linear layer, if your weight is 0, okay, this A is 0, you can see that the prediction is just a constant, right? It just depends on this simple bias, and you can choose this bias so that this equals to the pi 1. Pi 1 is just the marginal probability for symbol 1. Okay, this is not hard to realize. And you can show that with this kind of a construction, with weight tying, you can compute the Hessian for the full thing, which is very, very messy. Like, that's actually the hardest part of this. And you can show that it's almost like positive definite, using which you can show that it behaves like a local minima. And if you remove weight tying, and you can show that again the same configuration, Hessian turns out to be indefinite, from which you can derive that it's a saddle point. So this is like the overall high-level view of overview of how we prove this. Okay. So to summarize, so this is like the main picture I want you to keep in mind from this part is, it turns out if there is weight tying under this switching greater than 1, there are some bad local minima on the surface. And if you remove this weight tying, the same point behaves like a saddle point. Okay, so that's the main picture. Okay, so as some of you might be wondering, like, why? Like, maybe I'm considering some sort of like a theoretical, la la land, and this doesn't really happen, or yeah, maybe it's a esoteric case, but that's not really the case. There is a reason why we are doing this, and it turns out in practice that's exactly what happens. So here, what you see here is this is the local loss curve, okay, line, which corresponds to the entropy rate of the Markov chain. Okay, that's the global minimal loss, and the local loss corresponds to the entropy of stationary distribution that you saw. So it turns out that if you train with weight tying, it often gets stuck at local minima, as you see the red curve. And the moment you remove weight tying, almost often when you train the single layer transformer, it escapes this line and goes to the global minima loss. So this is what we empirically observe, which is in fact the motivation for our theoretical results. So we wanted to explain this phenomena, and that's how through the loss landscape we explain why probably this is happening. Okay, so that's the static picture I gave you. Okay, why this phenomena could be happening. So this covers one main part of it, where I showed how the optimization landscape looks like. But there is another equally important component that I didn't talk about, that that gives even a bit more perspective about how this goes about happening. Okay, so that we will see in the learning dynamics. Yeah, I have a question. Yeah.
Yes, so can you comment on what happens with multi-layer?
Sorry?
When you have multiple layers?
Yeah, that's a later part of the talk. I will touch upon. Yeah.
this local minima with the bad local minimum, what are the weights there? Are they zero?
Only the last layer is zero. Yeah, only this last layer, if this, so that means there are many configurations.
Okay.
Yeah, just as long as you keep this zero.
Okay.
And empirically, we observe that when it gets stuck at local minima, this vector looks almost like zero. In that case, it doesn't matter what they belong.
Sorry, I missed that.
No worries. Okay, so let's move on to the
one more
loading
question.
dynamics
Sorry,
part.
before you go on, and these results are independent of whether you overfit. For instance, let's say I used a large embedding space, or I use many parameters.
Yeah. This is
doesn't
independent of the dimension because
I see.
it's a first order Markov chain. Even with dimension 1, you can represent it because it's just a linear function.
No, certainly. But the question is whether with higher dimensions you might be able to get out of the local minima. You know, whether that might actually help you avoid getting stuck in local minima.
That's possible in principle, but at least for the reasonable dimensions, we tried this phenomena that we always observe. It could be possible that it could make it slightly easier, but the theorem that we proved is independent of any dimension. Okay, and for the dynamics part, so in principle, as you said, the depth could help a bit, but you see there's a much more important role being played by initialization that we'll just see in 1-2 minutes. Okay, so that basically resolves why this is happening.
Okay.
Okay, to look at dynamics, we specifically focus on the gradient flow. Okay, so just a quick recap, what is gradient flow? Here is that the time derivative of your parameters is the negative gradient of your loss. Okay, so here theta t denotes the set of all transformer parameters at time t, and L is the same next token prediction loss that we saw before. Okay, so here, if you recall, as I said before, theta denotes all the set of parameters, embeddings, positional embeddings, matrices, everything. And I don't know, if you were to do gradient flow for this entire set, it's just almost impossible because it's just too complicated. But luckily, some hidden hand helps us here, which is that empirically we observe that all these matrices that you see here and these embeddings, it turns out that they have rank 1. Okay, so like a beautiful phenomena. I don't exactly know why this happens, but turns out that when we observe empirically and print out the structures, they all exhibit rank 1 structure. Okay, meaning all these embeddings lie in some specific direction, and that direction turns out to be the like eigen direction for all these matrices. Okay, that's so. Using this observation, you can slightly reparameterize, meaning you can, without loss of generality, assume that your parameterization is a low rank parameterization. Then it suffices to just look at the scalars in those what do you say, in that low dimensional embedding, basically. Sorry. Yeah, low dimensional subspace. Basically, all you need to is track a bunch of scalars because everything stays in that space. And so the 3 main parameters that turn out that are enough is one is something called embedding scalar that denotes how much in a specific direction your embedding vector lies in. And this A is like an attention scalar that denotes the overall strength of attention. And W is like another weight parameter that's, that parameterizes all these matrices, and that's like the key term that controls this operation. Okay, this is, you can say this is like bit of a very, very big leap, but this big leap is what the empirical observations give us. And thanks to that, now it suffices to just observe and analyze these 3 parameters. Okay, there are 3 embedding parameter, weight parameter, and this attention parameter. So with this,
this is only for this particular Markov chain.
This is this all in the specific setting, first order Markov chain and a single layer transformer. Okay.
That is an experimental observation, or
that is an experimental fact that we observed, like various runs and everything, and that's what we are capitalizing to reparameter. Of course, it's a topic of interest to explain why these low rank structures emerge. Okay, that's a different line of, but that we didn't want. At this point, I'm happy to use that structure because we want to understand how the dynamics evolve. Okay. So with this parameterization, now the flow is over just these 3 parameters, just in the 3-dimensional Euclidean space. Okay. So to visualize how exactly the flow looks like, okay, let's start with the small simplification. Let's assume that this parameter is 0. It turns out that for first order case, this is good enough. but we'll revisit later if this is not 0. But let's assume just for visualization, if A is 0, that means there are only two scalars now, embedding scalar and the MLP, the W scalar, okay? So in this case, so how does the flow look like if you simulate it? So it looks like the following phase diagram. So let's take a moment to parse it. So there are only two variables, right? E and W. You can show, it turns out that the set of all global minima follow this kind of a, almost like a hyperbolic curve, okay, the purple one you see. And the set of all local minima are on this part of the x-axis. This is a saddle point, the triangle, and the set of all local maxima are this, okay? So as you see, there are some contour lines here, and there are some arrows here, you see. The arrows are the gradient flow directions, okay? And you see almost magically, this gradient flow arrows align with these contour lines. And it turns out that for this gradient flow, there is an energy equation, which is basically like the, like a potential that is constant, it's an invariant. If you're running gradient flow, it turns out this energy stays constant, so the flow always goes along these contour lines, and there's a closed form expression for this. Just I will not get into details about how we derive this, but the energy function there's a closed form expression for this. Maybe I'm missing factor of 1 or 2, but that's how it looks like. And that's what this flow magically follows. Okay, this is just a phase diagram, but that's not the full story. Okay, the important part is here. So if you see here, I shaded this region green, this red. And what these regions represent is that it means as long as you start your flow in this green space, you'll always converge to the global minima curve. Okay. But if you start your flow here, the arrows always take you to local minima. So here, as you see, the origin 0 lies in this green region. And typically in practice, that's how you do, like at least for the experiments we did all Gaussian initialization. So you see here, if you do Gaussian initialization with like some small ball, in this case, P plus Q less than 1, you see that the flow always converges to global minima. So this is one of the main reason why we didn't observe like this kind of pathological behavior for P plus Q less than 1, because if you're doing some standard Gaussian initialization, though there are some bad local minima, the flow takes you to the global minima. So that's like one of the key reasons that we can explain how the previous phenomena that I showed you, right? Okay. But now, surprisingly, not surprisingly, if you change this condition to switch this condition, right? The switching greater than 1, the same portrait just flips over almost. Now you see here, origin lies in the basin of, they call it basin of attraction, right? The whole red region is the basin of attraction for the local minima. And you see here, origin lies in this part. So if you initialize here, right, it will get stuck in some local minima along this x-axis.
Why do you have so many global minimas?
Because there are many realizations that could, there doesn't have to be a single one, because it's a, you can, there are many parameterizations that all give the same formula. So, often that's the case, right? Even for feed forward, like manifolds and all. In this case, there's just a simple parametric curve. So, so that's why this also explained the previous picture that I showed you, right? Like when you are doing some standard initializations, often it's getting stuck at local minima because precisely of this reason. So this also gives us some positive news, saying if you initialize in this region, right, even if P plus Q is greater than 1, you can still go to global minima, right? But that's what the flow says, and that's exactly we empirically check as well. Is we initialize in some region of like this, and it turns out that indeed you can escape this local law, and eventually this is the purple curve using this initialization, and you can get to the global minima loss even in this setting, like P plus Q is greater than 1. This we checked it for the full transformer, okay? The insights are derived for the small parametric case, but this experiment that we ran is for the full transformer model. So this highlights how some hidden structure is playing a big role here, and especially this gradient flow phase portrait. Okay. And So put together, we saw these two. If the switching is less than 1, this is how the portrait looks like with the standard initialization. And if switching is greater than 1, this is how the portrait looks like. But this is, again, under slight idealistic setting, in the sense here I'm assuming I know what the switching is. But often in practice, you only see the data, right? No one is telling you what the switching is, let alone it being Markovian, right? So let's say if it's a first order Markov, but you don't know anything about its switching condition. So you would ideally want some common region of initialization so that you can always go. And if you take a close look at these two portraits, there is some common region of intersection in between these two asymptotes. You see this yellow curve and this yellow curve. So this region is common to both these plots. So as long as you initialize in those regions, no matter what your input configuration is, the switching, you'll always go to global. Okay, so this is the overall takeaway for two variables, right? Just like the embedding and the weight parameter. You can do this for like the full Euclidean R3, and the picture looks a bit complicated. That's why I didn't start with this. But the main takeaway is that, so the local minima now looks like a plane, okay? You see near origin, and the global minima is like a sheet, the green sheet. So the main takeaway, again, to keep in mind, if P plus Q is less than 1, you can see that if you initialize in this near origin, it acts like a repelling field. You go to the global sheet. If P plus Q is greater than 1, you can see it acts like a local basin of attraction, so you get stuck on the local minima plane.
When P plus Q is equal to 1?
It's like a corner case. Okay, in principle, one could derive, but for the Hessian analysis and all, it's just, you have to, what we studied is something called like first order saddle, and you have to go a bit deeper. And it's not, okay, mathematically, it's not really interesting case, but we never bothered about it. Like, it's like a one corner case. I don't really, because these conditions are strictly required to show some positivity and negativity. But it's something interesting would happen, but I would presume it would be some kind of unstable something, I feel, because it's here there is something smooth. I think, yeah, it's on some, I don't know, edge of, I don't know what, something. Yeah.
Yeah, is the change in, as you vary P and Q continuously, is the change in the basin also continuous?
Yeah, it's a very, as you see here, this is a, yeah, there is a closed form expression for all these lines, okay?
Okay. So as you approach from either side, it should converge to the corner case. So as you approach from the greater than 1 and the lesser than 1, it should converge.
There is some, yeah, to answer the P plus Q equal to 1, you will see there is some clear flipping from the portraits.
Okay.
It's like gets close and close, but yeah, there is a small, this acts like an energy barrier, actually, these asymptotes. That's the reason why you cannot go from here to here. You can show that these lines is where, so this corresponds to this basically, yeah. These are like the, I think, infinite energy barrier, I think. That's why you cannot flip from one side to the other side.
Also in the next diagram, what happens to the regions between the red and the green? There's this.
Here it's a lot more complicated to analyze. So here, at least in 2D, we could partition fully into this, but in 3D, maybe if you have, I don't know, Wolfram 3D and like a lot of time, one could sit down and characterize each of these regions, but it's a lot more messier. Like partition the whole space into this kind of, this is the basin of attraction for this, yeah, it's very, very messy. Even for two variables, it was like very complicated, like partitioning like this. So it might be possible, but the question is it worth it? Like,
yeah, because it's very similar to a question on whether like three body diagrams. So which one, we say if you have a third body with a very less mass, which one does it eventually collide into? So it has a very similar basin diagram.
I see.
Yeah.
Yeah, maybe, yeah, it's possible, but yeah, we didn't have time that unfortunately to go into detail. Okay. Yeah. So that's the learning dynamics for this part that gives a clear picture, more clearer picture of what's happening under the hood. And yeah, so that concludes the first basic setting where we saw how even single layer transformers can probably fail to learn on this task, right? Yeah. But that's by the nature of it, right? Because you know the global minima, you have to realize the true kernel. Anything is, you can see you're learning a first order Markov chain. If someone asks you, okay, that's too complicated for me, give me something simple enough. What is the best? You see, the marginal is the obvious estimate, right? So that's why it's not surprising that it's intuitively speaking. Mathematically, you can go over all these things, but like intuitively, that's what you would expect, right? Yeah, like that's how the way to realize it, but
Yeah, I just have a question about this energy. So what is the theoretical reason this exists? Is there like some symmetry?
it's from the flow. We derive this directly from the flow.
But so it means that the system has some global symmetry, right?
The system has, sorry?
Some symmetry, right? In physics, that's when there's a conserved quantity.
This is okay. Like, so I don't symmetry means various things, like some flipping of the variables or something. So to me, the way I look at it is, yes, this is the invariant. The flow happens so that it always stays on this energy contour, basically. Never. You start with some initialization, so you have some initial energy. So the flow goes always along this initial energy curve, basically.
Okay.
The flow. This is empirically, yeah. What
you see, you see,
print them, basically you print them like matrices or something.
yeah.
If it's low rank, you can see it off, but you can do some heat map kind of a thing. You can see that it's uniform. If it's rank 1, there are only like 2 kind of one, either it fires or it doesn't fire, right? So this is how we can visualize, because it's also rank 1. If it's rank 2 and all, you need to dig a bit deeper and see which directions it aligns and all. But in this case, it's rank 1. So I would say we were lucky, but I'm happy to be lucky.
Yeah. And also, I mean, once you see that there is a low rank structure, can you simplify the layers a lot more and then still expect the similar,
Yeah. That's what the analysis, everything. Yeah.
Okay.
Could do that. Okay. So,
Well, so I guess again about this low rank structure. So in practice, do people do the simplification?
so not in this spirit, in this sense, because this is a very, very toy setting, you can say, because one layer transformer and all. But this something called LoRa people use, which is once you have a pre-trained model, in order to fine tune it, they add just like some low rank terms on top of it. How exactly that is related to this, I'm not really sure, but this kind of low rank ideas are being used in like fine tuning these models, because often in fine tuning, you don't want to, again, you don't have the resources of Google or OpenAI to run from scratch, right? You just want to fine tune on some small task. You want it to be computationally lightweight. So in this kind of, these low rank structures kind of thing, yeah, it's a natural idea, right? Like low rank has a very, very deep significance in various fields. So yeah, that kind of ideas are being used. Okay, so now let's move on to the second setting, where we still consider first order Markov chain, but we take 2-layer transformers. Okay, so here something very interesting happens is this popular emergent phenomena in context learning. You can see that this phenomena emerges already in this setting. It's a toy setting, but that you can already replicate in this scenario. And here we see, yeah, this shows like how even just one addition of one more layer shows how the functionality drastically changes. So now we'll take a closer look at this scenario, okay, for the next 5 to 10 minutes. Okay, just a brief primer on in-context learning induction sets that you already, that you might have seen yesterday as well. Like say you have some, again, passage from, text from Harry Potter, and if you were to predict what follows this, the notion of in-context learning is that that what people observe, if you take a pre-trained model and you just give it like this, the model just learns, figures it from the context that, yeah, wherever this past instances of this word has occurred, and then uses the one following it, right? Here it's lay, and uses the same thing for prediction here. So that's like the rough idea. This is a specific kind of in-context estimation. Okay, and people know that this kind of what do you say, behavior is due to presence of circuits called induction heads. Okay, I'll talk about them slow, but this is just an overall outline. So coming to our favorite Markovian setting, okay, so how this in-context estimation looks like. So let's take an example of, like say in this case, k is 2, okay, like say order 2. So if you were to do, if you're given an input symbol like this, input sequence like this, and you want to predict the next one following this 0, 1, a natural idea is you look wherever this has occurred and look at the symbols following it. So in this case, there are 2 different symbols. Okay, now you can say maybe after is a uniform distribution on these 2, one of them. Okay, and the main idea, as I said, you look historically where the same context as the current context as xt is there and use it to predict the next one. Okay, mathematically you can write it as following. So this notation means it's a kth order estimator at a given all the pass sequence, right, at a position xt, what is the next token probability. So here basically you look for those indices I, okay, where the past xi minus 1 to xi minus k matches the current context xt minus 1, xt minus k plus 1. Okay, if that's the case, I look at the symbol xi and I use it as a proxy for my next symbol. That's it. And you normalize it by all such matching occurrences because it has to be probability. But that's the main idea. It's like nothing fancy, just doing some empirical counting wherever the same context has occurred. Okay, and then you can ask if this is the like the in-context estimator and induction head realize this, how can transformers implement this mechanism? It turns out that to understand this again, this two-layer setting is very good enough, and you can show that how a two-layer transformer can realize induction head is the following high-level idea is first layer basically copies the previous token. So basically it tries to copy the parent information here, and the second layer tries to do this kind of a matching. So here it looks for this token A, right? This is the current token. It looks where this has occurred as a parent in the previous history, and then uses the token following it like B as its prediction proxy. That's like the overall idea, and you can construct weights so that you can realize this. Okay, it's a well-known result. Okay, so this is how you would realize a induction head that I touched about, that I talked about yesterday as well. Now, the natural question you can ask is, how do transformers learn this kind of mechanism, right? How do they learn induction heads? Okay, so here to look at them, just let's take a more concrete setting and look at how the data structure is and all. So here we consider what is called in-context Markov chains. Okay, this is a bit of fancy word, but it just means a random Markov chain. Okay, so the idea is, again, you have a first order Markov chain. Okay, the parent is just the token before it. To generate the sequence, what you do is first you generate this transition matrix or kernel randomly from some prior, like say some Dirichlet prior, which is a standard one. Once you have the transition matrix, then you generate, first S1 from some stationary measure, and then you sample the sequences from this transition kernel. Now there are 2 sources of randomness. One is your kernel because it has some prior, and once you have the kernel, you generate the sequence, which anyway is random. So that's the 2 sources of randomness, right? And but that's what, if you use this procedure to generate a Markov chain, that's what they call in-context Markov chains. Or if it helps, you can think of this random Markov chain. Okay? Because of, and a natural estimator again here is compute just the empirical transitions in context. The notion of in context is basically means you're just using your previous samples to adapt your estimator. And this is just a counting estimator that I just previously talked about. Okay, so this is a natural estimator, and that's what in context Markov chains are. And now taking a look at the architecture, what is the 2-layer architecture that we use to study? So here we consider something called disentangled transformer. Okay, so what do I mean by that? Here we consider the normal token embeddings and position embeddings. Usually you add them, but here we consider them side by side. Okay, we don't add them. And also wherever there are some linear operations, we just concatenate them. Okay, algorithmically this is how it looks like. Basically at the input level, you embed or concatenate both the one-hot encoding of your symbol and the position embedding. Okay, and at every layer, usually you add this attention output and the input like the residual, but here you just concatenate. Same you do for the MLP, and finally you return some linear operation. Okay, this is not technically how transformer does it, right? The operations, but you can theoretically show that whatever functions that you can express with normal transformer with some whatever depth and heads, you can do the same with this architecture modification as well. So it's like in some sense, like without loss of generality. The full classes are the same, but the underlying realizations are different. And we focus on this thing because it's easier to do theory for this, okay? And as I was saying before, definitely this is a completely impractical architecture because as you see the if you're concatenating stuff with every depth, it keeps exponentially blowing, right? The dimension gets doubled at every step, but nonetheless, it helps us to do theory and we can derive many meaningful insights. So that's the reason why we stick to it. But at the end of the day, this is without loss of generality because the two classes are equivalent. Okay, so this is the architecture. Now let's look at what happens if you train this disentangled transformer on this in-context Markov chain. Okay, so this is how the overall attention patterns, everything looks like. So here there's a lot going on. So let me walk you through all the important parts. So the first part, as you see here, is this the causal graph. As I said before, this is the first order Markov chain. So the dependency is just shifted by position 1. So that's what you see. This is the causal graph. Here there is no learning. This is just how the Markov chain structure is. Okay, this is how you can visualize it. So it turns out that if you train this disentangled, the attention layer you see here, it almost exactly learns this adjacency graph structure. This is the attention pattern you see. At each position, you see which position is it attending to. That's the heat map. And you see that this almost encodes this causal graph structure. That's like the first main important observation. Okay, so more concretely, if you take a sample sequence, let's take a look how this happens. Okay, if let's say your input sequence is the following: A, B, A, C, B, A. So what first attention layer does is copy each parent. So what does it mean? So for each of the symbols, these were the parents, correct? So for the first attention, it copies them. Okay, so that's the task of it, and it also okay, yeah. So that's the task for the first attention. Now going to the second attention, it needs to do this comparison and this to match wherever the parent has occurred before and to do counting. So how it does is, let's say you are at this position, right? Your token is what? A. Now I look wherever A has been a parent in the past. So these are the positions where A has been a parent, correct? Because A was a parent here and A was a parent here. So these are the positions where A had been a parent for. Then what are the symbols following that? It's B and C, okay? Now the task for second attention layer is to, combine them in some like one-hot encoding addition, but this is what, for this position token here, this is basically like my proxy for what I need to predict for the next symbol. That's what the second attention layer does, and this is how the pattern here firing is synonymous with this. Okay, so that's what the second attention does. And the same you can check for every position. So let's say this position B, your token is B. You look where B has been a parent here. So now what was the symbol following it? A. So you copy A here. You keep doing this for every position, and that's how basically you keep track of all the in-context matching stuff in this two attention layers. And finally, you need to read out, right? Because you just need symbol probabilities for each of these tokens in the vocabulary. And so at this position, what you do is, if I were to predict the next symbol, right? Since this is my kind of a proxy, I will say with half of probability it could be either of them, because that has been the occurrence in the past. So this is like the overall, structure, how the attention map captures this kind of an induction head. If you train this two-layer transformer, this is at the end of training. Okay, at the end of training, this is how it looks like. Okay, and the overall, these are like the firing patterns that correspond to what I just showed before. But for the analysis, we only focus on like some very sub-blocks because that's the most important aspects of this dynamics. And in particular, this here is the focus is to show that this learns the graph, and here that, it corresponds to some kind of this kind of mechanism. But the main result one could show in this setting, you take the, again, this is the cross entropy loss. If you recall, this is the next token prediction probability, and this is the past, entire past. And you take the cross entropy loss for the full sequence, and you take expectations both over your sequences and also your priors, because prior is also a random thing. And the main result that follows, you can show that if you do some kind of a two-stage gradient descent step, the final loss that you obtain compared to the optimal loss, it decays like with polynomial in T. Okay, up to some, you assume something about your Markov chains, which is always the case. And the main important thing is that first layer attention pattern, you can show that it's very, very close to the adjacency mat up to some error. So that's like the main result that one could show using this disentangled transformer, how it learns the induction head structure, and particularly how it encodes the causal structure input. Okay, and as a corollary, it all follows that whenever you train transformers on this in-context Markov chain, you learn an induction head mechanism. So that's how they exhibit this in-context learning behavior. And so another takeaway, the way to interpret is, though you trained it, let's say on specific class of priors or certain transitions it has seen during training, at the end of the day, it is doing a in-context estimator, meaning just an input-dependent estimator, right? You give it a sequence, it's doing some sort of counting just based on your input samples, right? So one could show that, so no matter what your sampling distribution is, basically this kind of an estimator, it is almost very, very close to the transition true kernel. This is just some mixing. This is just a Markov chain. If you take enough transition, if your sequence length is long enough, basically the empirical counts converge to the ground truth. So this is that kind of a result. But the main takeaway for us is that even if you train this induction out, even if you do this kind of training on some specific set of sequences, this implies that it generalizes to out of distribution sequences. So it exhibits generalization by virtue of learning an input dependent mapping. Okay, it's because at the end of the day, the function is something, just a sample of function of your input sequence. So that's the main takeaway from this part. Okay. So, and the proof sketch, I might have like 15, 20. Yeah. Okay. In the interest of time, maybe the proof sketch, I will give like a 1-minute teaser for this, which is the main idea is you can compute the gradients like for these important blocks, and you can show that it behaves like some chi-square mutual information between these two nodes, and okay, the negative chi-square mutual information. And so using, okay, for this chi-square mutual information, right? For this Markov chain, it turns out there is obviously there's some kind of a data processing, meaning it's maximized across like the most recent thing, which is exactly for the parent. If you're looking at the node S6, it's maximized for the together with the node S5 more so than S4, right? This is a classical data processing inequality. Using this idea, you can show that when you're making these gradient steps, eventually it learns to point along this. It learns to capture the attention mechanism that is peaked at this kind of a transition more so than the other. So that's like the very, very high level idea. Okay. And eventually, basically it learns to capture this kind of an adjacency graph in an induction head. And if you have a bit more complex, so the one I showed is the causal graph is just a parent before, but you can have parent anywhere else as long as it's just one parent. It doesn't matter where in the sequence is it. So in some sense, some other causal dependency, as long as it's still Markovian, you can still do the same. In which case, this algorithm is very, very similar to this famous algorithm for learning tree structured graphical models, right? Where it uses the mutual information to maximize which node to attend to. Okay, so that's like the very high level overview. But anyway, the main takeaway, as we saw here, is that even in this simple setting using a two-layer transformer, we could replicate this in-context learning behavior. And in particular, we saw how transformer learn these induction heads. Okay, but there is a small. This is what I talked about so far, right? For this second or first order memory so far. So you can ask, what happens if I take arbitrary memory sources, like a memory is K? So in this case, let's say I take like a 3 gram, right? Like in this case, S4 has like 3 parents. So 3 gram means 2 parents, right? One is S3 and the other is S2. If you have like a more than K is equal to 1, so how do transformer learn this kind of more complex causal structures? So there's a natural way to extend previous results is that earlier I was just showing like one attention head, meaning there's only one attention layer. There is some practice people use multi-head attention, meaning there are several attention heads in parallel. So if you can use multiple heads, in fact, you can capture this again, a Markovian thing. The idea is very simple. Each head attends to one of the parents. That's it. So far, I was just talking about one parent, right? The previous node. Now you attend to multiple parents using these multiple heads. Empirically as well, you can see if this is your causal graph, meaning there are two parents, the first head learns to attend to one of the parents and the second head learns to attend to the other parent. And this you can observe for like various n-grams and so forth. And there's a learning dynamic result along the very almost similar flavor to the result that I showed before, where they analyze for this setting, assuming if you like what is n-gram and you have sufficient number of heads like n, let's say, and overall dynamics, you can show something similar. It learns an induction head and so forth.
Yeah. So how do you define in-context learning in general, and what is it for this? What is it for the case of this this random Markov chains?
So in-context learning here means given a sequence, I need to estimate the prediction probability just based on my sample sequence. That's what it's more so than learning. I would say it's, let's call it in-context estimation. Okay, given a sequence, you need to estimate its predictive probability just based on the sequence. So that's what it means. And we saw why it does it, because it learns a mechanism which is called the induction head mechanism that mimics the second order counting for this.
And what is like the more general definition, like outside of this context?
I don't think there is a specific definition from in-context learning, because this comes from a blog post from Anthropic. I didn't define it anything. It's a loose word, so to speak. Even I don't like the word in-context learning because it's like kind of ambiguity learning. It's not like learning, but the main idea is that if you take trained models, okay, BERT, whatever, GPT, they observe that even on some unknown task, they naturally kind of learn to do or whatever, figure out what to do just based on the input.
Yeah, like in the input you can give instructions.
Instructions kind of, and just automatically figures it on the fly.
Right.
That's what they this in context refers to that.
Yes.
Learning refers to that ability, okay? But here learning could be confusing because we are studying learning dynamics, so which means a different thing. But think of it more as like in context estimation or something.
So are you saying that the context is the underlying Markov chain that is?
Here the context is underlying Markov chain.
I see.
In this case, it's a very clear meaning what that in context estimation has to be, which is the second order counting, and we does it.
Right. But because the structure, there is a lot of structure in the underlying chain, it should be a easier.
In this case,
right?
There's a structure here because we want to do theory, right? Like practice, it doesn't care about theory, right? Like language doesn't care about it. Language has its own structure, but the models learn to capture whatever is relevant for the task. Whatever it is that you have to study, but that's the high level idea.
Thank you.
Okay, so now I need to slightly speed run, but it's doable. Okay, so far I showed you how at the end gradient descent learned induction head, right? This dynamics and so forth. But I omitted a very crucial component is what happens during the process. Okay, I just showed you the final result. It turns out that in course of figuring out this induction head, there's something interesting happens, which is some kind of a stage-wise dynamics, or some people call it saddle-to-saddle dynamics. Okay, so what exactly is it? So this was first observed in this paper for our old friend, first order Markov chain. So here this is the simple like transition diagram. Okay, there are 3 states. You flip, you switch between them some probabilities, and again in context, meaning there are several transition kernels possible. Okay, you remember the context. There are several kernels, and from each of them you generate a sequence. So what they observed during training is something interesting. So let's take a moment to parse this. So what they are plotting is the KL divergence between some distribution. Here there are 3 distributions and the underlying model. So the blue curve corresponds to uniform, just a uniform prediction. Just in the beginning, the model loss is very close to this, meaning in the beginning, it has nothing, it doesn't know anything, so it just predicts uniform probability. And later during the course of training, you see the orange curve drops. So unigram means marginal, okay? So you see for the good initial stage of training, the model is just predicting marginal probabilities. Then eventually this loss rises, but the green curve drops. The green curve is the actual bigram. Bigram is this first order Markovian distribution. So you see there is some kind of a stage-wise, first it's figuring out the easier relation to capture, which is the marginal. Then eventually it's figuring out the complex relation. Okay, so to understand this in more detail, especially theoretically, so the following work try to analyze it. So they consider generic n-gram, meaning that means the memory is n minus 1. Okay, that's just a notation. And consider again the disentangled transformer we saw, just 2 layers, but with n heads, okay, just for simplification. So they observe the following picture. So if you're training to learn a 4-gram, they observe that the loss goes through these many stages. First, yeah, so the unigram, and then it gets stuck at bigram for a while, and then goes to trigram, and then eventually drops, and yeah, eventually somewhere close to 4-gram it reaches. And the main question that one could ask, and they ask as well, is why does training linger at these plateaus that you see here, right? Like what happens exactly? And they show that, and a very interesting result that I alluded to before as well, these plateaus actually correspond to sub-n grams, okay? So what do I mean by that is mathematically you can show that there exists a realization of parameters for this transformer so that it can indeed represent a k-gram for all this k less than n. Like in this case, if n is 4, trigram, bigram, everything, then you can also show that it's almost like a stationary point, this realization, in some large limit, okay, length and parameters, everything going to infinity. They show that, each of them acts like a stationary point, and that's why this kind of plateaus occur. Yeah, this is again giving a static picture. They're only explaining the landscape. They're not explaining how it goes, jumps from one to other, but nonetheless, this is a very important insight, is that this plateaus occur because of the sub-n grams, okay? And that's what we observe, and empirically as well. Initially, when you're training, there is no attention pattern. It's just like, doesn't learn anything. But at this plateau, you see both of the heads, there are like 2 heads, okay, head 1 and 2. They attend to the same parent, okay? And eventually, one of them learns to attend one parent, the other learns to attend the other parent, corresponding to the bigram. Okay, so that's what we saw so far with all this, like a kth order memory and general number of number of head scaling with this memory almost. So it looked like the folklore knowledge was that maybe these heads should scale with k, right? Like if you are or the depth, right? Like whatever. That's how it looked like a fact of, I don't know, like a street fact. Something has to scale with k. But what we did was we even took like small layer, 2-layer, 3-layer transformers, and we trained it, like say for example, 8th order Markov chain, 4th order. What we observed is that if we train it like forever, eventually they almost get close to the optimal loss. Okay, so this we observed empirically, which kind of motivated that something interesting has to be happening, right? It's not obvious that a 3-layer transformer can learn, like, I don't know, orbital, like 8th order Markov chain, because people earlier couldn't train to this order. Like 8th order Markov chain looks, 8 is like a small number, but 8th order Markov chain is like something non-trivial, I would say. So, but in this case, it's all one head. Just 3-layer transformer, just one head per layer. Okay, everything constant. So that was the surprising part. So then, we set about analyzing, and then we show that there's something interesting happening, which is that to represent this kth order in context estimator that I showed like few slides before, right? To do this kth order counting, it suffices that all you need is just 3 layers. Okay, everything is just like one head per layer using some standard encodings and so forth. And with just constant depth, you can capture any kth order Markov chain. So this is a very surprising result to us as well, but that's what we show, is that 3 layers, you can do any kth order. And here, very important point to note is that here we are using this layer norms and stuff. And if you remove them, you can show a very tight lower bound that you need at least logarithmic depth. Okay, and one of the reasons why many of the earlier works probably missed is because of often for analysis, you remove non-linearities like MLPs, layer norms, and so. So if you have attention only transformers, then it turns out that you need like logarithmic depth. So there is some non-trivial role of non-linearity being played here, which really helps us to get to constant depth. And the very high-level idea is that the first 2 layers help you capture this kth order context, and this idea uses the smart way of combining the context into some Euclidean vector. And the layer 3 does this normal notion of counting and matching. Okay, that we saw before. So this was the main result, last year. But last few months, we showed that you can actually even get it down to 2 layers. You don't really need 3 layers. You can almost get away with 2 layers, but this is an archive. It's not yet published. But if anyone is interested, you can take a look. Okay, so that's like the overall picture for kth order Markov chain, where you can almost capture it with just 2-3 layers. And so here I only, the main takeaway is that I showed even with how shallow depth you can capture this. But learning dynamics are still open. Okay, this is very, very hard. Like it looks like a 2-layer transformer, but I don't know. Sometimes the simplest things are the hardest, right? So in this case, even for 2-layer, it's very, very complicated, but that's something open and up for grabs.
So I have a question, Ashok. This result you just showed about this K 3-layer transformer learning this kth order. Maybe I didn't understand correctly. So there are these bounds, I thought, on limits on of composition of transformers on compositionality. So if you take a function that has sufficient number of compositions, then you need a depth which scales with the number of compositions. Is this avoiding that function, that result using non-linearities, or is this a slightly separate context?
So it's a good, but I have to check, because often for this separation results, they use a very specific kind of, they assume some structures on the attention, like they remove some maybe non-linearities, or sometimes they assume that the attention is like hard attention, meaning there are only ones and zeros, like there is no soft attention. So I have to check, but at the high level, I think they could be orthogonal, because this is not really like a function composition, right? Kth order counting is like
can the k plus one term be an arbitrary function of the previous k terms? I mean, if that's the limit of what you're doing, then it would relate to the compositionality result, right?
Sorry, can you repeat the last?
Sorry, the question is, if you give the transformer an input which consists of a sequence of length k, can the transformer be learned to to output an arbitrary element of the alphabet, which is a function of the k of the sequence that you input?
Okay, from the universal approximation result, yes. Okay, the very, very first result, but
no, in this with 2 layers, not.
I don't think so. I'm not sure. Yeah, because even for Markov, this was like it came as a surprise to us. Okay, but it could be possible that because its Markovian structure is special, any arbitrary function, I would be very, very surprised that 2 layers can do it.
I see. Okay, thank you.
Okay, so this concludes the Markovian part. So in the due to some time constraints, I didn't cover some other interesting works on the Markovian space, which if you're interested, you can take a look. We have first one, attention, explain some phenomena called attention sinks that happen in practical training of transformers. They use this again Markovian setting. And there's something called interleaved Markov chain. So far, I only showed a sequence generated from a single Markov chain, but what happens, they're generated from 2 different sources, but you interleave them. Now the model has to figure out even which Markov chain it needs to attend to. This and another, you can say, meta layer of in-context estimation. So this another follow-up work that tackles this, but in the, I didn't cover them today. So this covers the Markov part. Initially, I planned to cover another structure, topic models, but since we have a few minutes, I will just give a very high-level takeaway. What happens? So topic models are like been around for like a long time, like from the classical LDA and so forth. And what people observe often is that in practice, many of these pre-trained models like BERT and so forth, they exhibit like a topical structure, meaning if you observe the similarities, word-word similarities, they observe some kind of a block structure. Like here, these 3 correspond to like frog, toad, and lizard. And here it's like Beethoven, Mozart, and Schubert. So they see that as long as they belong to some specific topic, there is some kind of block encoding happening, meaning they're capturing some kind of a topical structure. This is for some pre-trained models. So there is a work that studies how using LDA, right, how this topical structure could be captured. And the main, where is the takeaway? So you can do the gradient analysis and everything, okay? And they show that even a single layer transformer with gradient analysis, you can show that the similarity between same topic is more than the intertopic up to some constant. So it's always strictly greater than this topic. So you can do using some gradient descent analysis. And the final takeaway from this is that this kind of a topical structure could be encoded in both the token embeddings and self-attention. And they show how this attention layer encodes this kind of thing in a 2-stage process. Okay, this is like the overall takeaway from the topical models. And then there is another recent work, very interesting, on something called factual recall. So what exactly is factual recall? So you might have played around with many of these models. Often these models act like a databases of facts, right? Like if you ask some specific questions, it spits out right answers. And somehow basically this kind of factual associations are stored in their weight somehow, right? And the goal of this work is to understand how do LLMs store these kind of facts, and what is the capacity, basically how many parameters do you need to store these facts. And the main result is that they give a formal model to study how transformer learns to capture this factual recall using something called associative memory. And in case someone who is familiar with the history of neural networks, they have very close connections to Hopfield neural networks, who recently won Nobel Prize in physics, Hopfield. And anyway, and the main result they show is that transformer can almost memorize facts with near optimal capacity as a parameter. Basically, they can store as many facts as they have as many parameters. So that's like the main takeaway. And they do gradient descent analysis using some, yeah. So the slides, everything there in the, the link I post, so you can take a closer look later. But the whole task could be like formalized, like let's say in this case, capital of France is Paris. So you can think of it as subject, relation, and object, the answer. So one could study how transformers learn to solve this. And yeah, so let's and here as well they observe something called a stage-wise dynamics, where in order to predict an answer, you need both the subject and the relation. You need both France and capital to answer Paris, right? They observe that sometimes it does suboptimal prediction. Basically, it spit out names of cities based on relation. Relation is what? Capital, right? So just looking at capital, it's outputting, I don't know, Rome, Paris, Delhi, something like that, without looking at the subject. So that the show is like some kind of a local minima kind of a thing. That's what referred to as hallucination, right? Because it's not listening to your question, it's just outputting whatever. So this is Jason's to Ishan Nichani, and this is very synonymous with the stage-wise plateaus we saw before. Okay, that's the main takeaway from this. And yeah, okay. So finally, the small important part I would like to conclude with is the generalization, because it feels very important. Just yeah, 2-3 minutes. So okay, coming to the final part of generalization, where we want to understand what are the properties exhibited by the solutions learned. So here, the quick recap, as we saw in both the parts. In the first part yesterday, I talked about the representation results, right? Like how various bounds we could use. And in particular, we saw provable benefits of using either depth or chain of thought. So here we would like to understand what happens. Basically, here we want to understand the questions that we didn't address before, like how does length generalization benefit from either of this? And in part 2, where we saw how gradient-based methods can reach certain local or global optima. So here the thing to keep in mind is various optima could exhibit various generalization properties, right? It's a well-known thing. So overall, we would like to understand how generalization happens. So in the part 1, for the representability, so coming to length generalization. So here the goal is that if you train on some small test sequences, we ideally want them to generalize to very long sequences during inference. And it's well known that transformers really struggle at this task, right? Even on some small toy tasks. So the one main thing to keep in mind here is, like, while designing metrics, like what is the right way to look at this generalization? Like if you take parity task, one thing you can think of is maybe you care more about just the counting addition more so than, exact whether it generalizes over long sequences, right? Because it depends on your downstream, task of interest. So what is like the right size of measure you want to look at where you care about generalization? And there is here main thing takeaway from this part is there's a very cool set of ideas that are slowly emerging. So far, like if you looked at automata yesterday, as you saw, automata and RNNs, they have a natural synergy, right? They have like almost a close equivalence, like the programs exhibited by automata, they could be easily represented by RNN and so forth. So there is a similar question you could ask. If you think of transform as a computational machine, what is the natural formal equivalent? Like what is the logic expressed by like a transformer, like a computational machine? So the main idea behind the first such paper to come up with is called RASP. Okay, it's called Thinking Like Transformers, which asks the question of what kind of programs can transformers compile, and it tries to show some equivalence. The recent follow-up to that, not so recent, okay, 2 years, but it's an interesting idea, is something called RASP-L. So the conjecture based on a lot of empirical experiments is that almost often in all these experiments, they observe that transformer exhibit length generalization to some long lengths only if there is some short RASP program to describe the task. It's a very cool observation as a formal way of looking at it. I will not get into details, but that's a very like conjecture they put out there. At least empirically, they observed this to be true. Okay, and the main takeaways, again, very short, is people observe that the various length generalization issues for transformers often because of these positional embeddings, because yeah, if it has to generalize to unseen, it's difficult. And also there is some kind of maybe some new hierarchy imposed by this kind of new perspectives, because yesterday if you saw both these tasks belong to this TC0 minus AC0, but using this framework, one could actually show that this task is a lot more easier for generalization compared to parity. So this kind of new viewpoints are very important. And this is RASPEL, okay, 23, but there is even follow-up work. Apparently this obtains the tightest bounds. You can show, basically it gives the tightest hierarchy for these transformers. It's something called CRASP, which is also another programming language, which is naturally aligns with transformers. Okay, so you're interested, take a look. That's for the length generalization. So coming to same length generalization, meaning the length is the same, but you're interested in see how it generalizes to out of distribution sequences. Okay, so it turns out that models, even on some simple, very simple task, these models fail to learn robust solutions. And one such task people have observed is something called flip-flop. It corresponds to like some read or write operations on a 1-bit memory unit. Okay, it's like it's a very simple automata. Right? It has 4 states and so forth. And they observe that it can represent it well. Okay, it can learn well, and if you test it on some other sequences in the same distribution, yes. But even like if you slightly go out of distribution, it like fails miserably, and which is very surprising. Maybe not, but for like it's a very interesting phenomena they observe, and they observe it has to do with attention mechanism has some inherent limitations. Basically, this kind of tasks expose why these models fail on certain kind of things. So this is another thing to keep in mind. It's very important how, if you were to achieve generalization, what are some failure modes and how we can mitigate them. And to just a very high level summary, so we saw all through all these parts, right? What are some important questions? Like in part 1, we saw what could we realize, and in part 2, how do they learn them, and in part 3, how do they generalize, right? Like to various length generalization and out of distribution as well. And we also saw many clear insights coming from them. In part 1, we saw how the depth hierarchy is based on these complexity classes. Here we saw like some kind of like a stress test diagnosis, right? We saw even for the very simple scenario of learning a first order Markov chain, these models fail. And finally, we saw how we could change some structural constraints in these models to improve out of distribution generalization and so forth. And at the same time, this is not the end of story, because sandboxes are a way to look at it, and there are some limitations as well. And often in practice, like the main question is what is the right kind of abstraction you want to use, right? Like so far we consider some simple models like Markov, topic, and so forth, because they have been studied for decades, right? Like, but what if you could use some more complicated, like a mixture and so forth, to model language on the data side, on the model side as well? We have to make certain choices, right, for the analysis. But what are the right choices to make from a broader perspective? Because apparently in practice, people observe that for the models, pre-trained models on internet data, they learn to capture some kind of a Fourier features, okay, which cannot be replicated for some small synthetic tasks. So here again, what kind of, how do you translate these practical insights while modeling? That's also another open question. And yeah, so to cut the long story short, there are many interesting insights to be gained from this, but also there is a lot more to do. And yeah, we need, of course, a broader community involvement to solve many of these complex tasks. And yeah, with that, I conclude the talk.
Thanks a lot, Ashok, for the wonderful talks. in the interest of time, we will now have coffee, and I think we can start at 11:30. Andrea, for the next talk.